What we're looking at here is the differences between inelastic and elastic collisions, but there's formulas. That's what we're going to be looking at. Now, in terms of inelastic collisions, momentum is always going to be conserved. So we can just use our conservation of momentum formula. And in most cases, you will need to have three of the velocities and you would be solving for the fourth velocity. Now, in terms of kinetic energy, we can use our kinetic energy formula over here. And what we're going to find is that the kinetic energy before does not equal to the kinetic energy after. So in mathematical terms, the left side does not equal to the right side. And that is in terms of inelastic collisions. Now, perfectly inelastic collisions, the momentum is also conserved, so you can also apply the conservation of momentum formulas above. But what happens to that formula is that it becomes more simplified because the two final velocities now are the same. It becomes as this formula over here. Now, you can think of inelastic collisions as basically when two objects are colliding, they are in love. So that's why we call it an inelastic collision, because they are sticking together and they both have the same final velocity. Now, in terms of elastic collisions are a little bit more, there's more cases to elastic collisions. Now, the momentum is conserved, so we can obviously apply our momentum formulas. The kinetic energy is conserved as well, so we can apply our conservation of kinetic energy formulas as well. And these are just generalized cases. Now, we can get a little bit more specific in terms of elastic or perfectly elastic collisions. Now, when we combine the kinetic energy formulas and the momentum formulas, there's a lot of derivations. Your textbooks will show you how these are derived. We will get two formulas, one for object A and one for object B, or object 1 and object 2. We will have two formulas. There will be final velocity for the first object and the final velocity for the second object. Now, we can simplify this. If one of the objects is at rest to begin with, then, for example, if object 2 is at rest, this entire part of the equation will cancel, and we will be only left with this part of the formula. It also simplifies for object 2 as well, and that's only when one of the objects is at rest. Now, there are three special cases in terms of elastic collisions. The first one is when objects have the same mass. So when objects have the same mass and they're colliding with each other, we will look at that simulation over here. So over here, we have a kilogram object and another kilogram object, but they're going at different speeds. One's going at 6 meters per second, the other one's going at 3 meters per second. We're going to let the simulation run. The two objects are going to collide. And notice how now they have switched velocities. They are now in opposite directions. So what happens is that they exchange velocities upon contact. Now, if this case scenario was when an object has the same mass, 1 kilogram and 1 kilogram, and they are colliding with each other, except one object is at rest. So object B is at rest. We're going to see what happens. So notice how now object 1 now exchanges velocity. Now object 1 becomes at rest, and all of that energy, all of that momentum is transferred over to object B, and object B now moves at 10 meters per second. So both case scenarios are the same, except this one is just a little bit more specific, where we're looking at an object that is at rest. So they're exchanging velocities. Special case 2 is when mass 1 is a lot smaller than mass 2. Mass 2 is a lot bigger. So we can see what that simulation will look like, where we have mass 1, which is kilogram, and mass 2 is about 50 kilograms. And we're going to run this simulation. And you can see that object 1 basically returns back. So it's like action reaction, it just reflects back. And object B is still moving, but it's moving very, very slow. Now, in reality, for this case to occur, when we're comparing mass 1 and mass 2, we're talking about mass 2 being a lot larger. So this would be like a case like a tennis ball hitting like a big truck, and the tennis ball bouncing off of the truck and the truck barely moving. And in terms of comparison, usually mass 2 has to be 600, 500 to 600 to 1,000 times larger than mass 1 in terms of this to occur. So basically what happens is object 1 as becomes, it goes in the opposite direction. It still has the same magnitude, but now in the opposite direction, so it's now going to be negative. And object 2, which is at rest, continues to stay at rest. Now, special case 3 is when object 1 is a lot bigger than object 2. So it's a heavier object colliding with a much lighter stationary object. So over here, we have a 50 kilogram object, which is going to collide with a 1 kilogram stationary object. And now you can see a lot of the momentum was transferred over, and both objects are moving in the same direction over here. So in terms of this, the first mass will continue at nearly the same speed. And over here, it was going at starting at 10 meters per second. It's about 9.61, so fairly, there's some loss, some sort of energy which is being transferred over, but it's approximately the same. And object 2 is going to be almost twice the original velocity of the first mass. Usually object 2 would be in motion, and then it would be continue to move in that same direction.